Somewhere around 2800 before Christ, in the ancient city of Babylon, someone discovered something interesting. They were boiling animal fat, probably from a slaughtered cow or goat. And at some point, wood ash and water got into the mixture. And what came out was something that lathered and bubbled at the same time. And something that was fundamentally different than what came in. So you may be wondering, how can something oily, like a fat, convert to something that actually bubbles? So they wrote it down on a clay cylinder. Archaeologists found that cylinder thousands of years later, and what it describes is that fat, ash, water, and heat is saponification, the same chemical reaction we are using every time we make soap today. That's the story I want to tell in this video. So the earliest written recipe we have of saponification comes from ancient Babylon, where they basically write that when you mix animal fat with wood ash, water, and apply some heat, then you get something that actually lathers and cleanses. Basically, wood ash is rich in potassium carbonate. Then potassium carbonate together with water would produce potassium hydroxide. So you would get basically a solution of potassium hydroxide, water, which was also not that pure. It consisted of other impurities coming from the wood ash. And then they would take this potassium hydroxide lye, they would mix it with animal fat, they would apply heat because heat basically speeds up the saponification reaction, and they would get soap. Let's look at the saponification reaction. All these animal fats and also the vegetable fats like coconut oil, shea butter, olive oil, castor oil, and so on, they contain what we call triglycerides. Triglycerides are basically fatty acid chains bound in a glycerol molecule. So you have 3 fatty acid chains bound in a glycerol molecule. So when we say olive oil, actually olive oil contains oleic acid. Oleic acid is a fatty acid, and what we mean with oleic acid is that we have 3 molecules of oleic acid bound together in this glycerol molecule. Coconut oil contains lauric acid. Lauric acid is another fatty acid, and when we say coconut oil, we basically mean the triglyceride of 3 lauric acid molecules bound together with glycerol. So when we add a base like either potassium hydroxide or as we will see later, sodium hydroxide, basically what happens is that this hydroxyl group, which basically determines how basic a substance is. So when you see this hydroxyl group, it means that you have a very strong base. This hydroxyl group is very reactive, meaning that it's very looking forward to break chemical bonds. So when it sees a triglyceride, it comes here and it attacks the bond between the glycerol and the 3 fatty acids. So the glycerol molecule basically gets released, and the 3 fatty acids now react with the sodium or potassium atoms to create soap. That's why the saponification reaction is oils plus lye equals soap and glycerol. So glycerol is basically what makes soap very moisturizing because it's a humectant, it traps moisture into the skin, and it's there to protect our skin from drying out. And soap is basically what cleanses, because so as we will see here, basically soap has basically this hydrophilic head, and the hydrophilic head means that it loves water, and then it has this hydrophobic tail, meaning that it loves basically oil and apolar substances. So basically this hydrophilic head will bind with water, and this hydrophobic tail will bind with oil grease. And by the way, one of my biggest passions is creating minimal skincare that works and that is functional. That's why I developed a free PDF system that shows you how you can make 6 different skincare products with only 7 ingredients, because I want to prove to people that you don't need to buy 100 different oils to make soap or other skincare products. You only need a handful of ingredients and oils to make many different skincare products that actually work. If you want this, comment Perry, I want a formulation system, and I will send to you as soon as I see your comment. And here's what I actually learned while researching for this video. Potassium hydroxide and sodium hydroxide, as you know, they are alkaline. They are an alkali. That's how it's called that's what we use, the term we use in chemistry, which means a substance that is of a very high pH, of pH 14, and a substance that is very, very basic. And basically the word alkali comes from the Arabic word al-kali, which basically means ashes. So wood ashes, they basically contain potassium carbonate that then converts to potassium hydroxide, and they are very alkaline, and that's why we have this word today in chemistry called alkali. So basically for years people would make soap in that manner, basically passing water through wood ashes, filtering it slightly out so that it's not very impure, and getting this basic solution that then they would mix with animal fat. But the problem with this is that it was very inconsistent. You didn't really know how much lye your water had inside, and you also carried some impurities from the wood ashes in your soap. Now let's talk about Rome, ancient Rome, and the word soap. There is a legend, this is not confirmed, but I really like the story of this legend, that there was a mountain called the Mount Sapo, and in this Mount Sapo they would make sacrifices to the gods, and they would sacrifice animals, and basically the animal fat with the wood ashes from the fires plus the rainwater that would fall afterwards would create soap. And they say that this is why the soap was called soap, because it comes from the sacrifice that were made in Mount Sapo. So the problem with wood ash is that the strength of the alkali would basically vary from batch to batch. It would either be too soft or too harsh, making saponification very unpredictable. Before we get into modern soap making with sodium hydroxide, as we will see soon, back in 1865 we had the first US patent on liquid soap. Liquid soap was patented by William Sepfard in 1865, listed as an improved liquid soap. Notice the word improved here. This was not a patent of the first liquid soap ever. There was liquid soap before that. This was just an improved liquid soap recipe, where he discovered that by mixing common soap to a large quantity of spirits of ammonia, you obtain a liquid soap of superior detergent qualities. So for most of history, the strongest alkali we had was potassium carbonate. It was inconsistent, it was not pure, and it was not scalable. So in 1791, Nicolas Leblanc developed a process for manufacturing sodium hydroxide from common salt, making lye more purely available. The Leblanc process used salt, sulfuric acid, limestone, and coal to produce sodium carbonate, which could then be converted to sodium hydroxide. The only problem was that it produced dangerous chemicals and residue in the process, leading to a growing problem with pollution. But then in 1863, Belgian chemist Ernest Solvay developed a cleaner alternative, reducing the cost and the environmental damage of alkali production. So now we have pure sodium hydroxide, and pure sodium hydroxide in dry form became commercially available to home consumers in the early 1900s. And most housewives who made soap at home quickly basically replaced the wood ash method with pure sodium hydroxide, because they could make something that was more reliable, consistent, and with less impurities. Which brings us to the final chapter. What is soap? Legally and chemically, the definition is very, very specific. According to the FDA, soap is a product in which most of the non-volatile matter consists of an alkali salt or fatty acids, and whose detergent properties are due to the alkali fatty acid compounds. That's the definition. Basically, alkali salt or fatty acids. Basically, soap. So anything that comes from the saponification reaction is allowed to be called soap in the US. In Europe, it's a bit different. In Europe, you can go to supermarkets and you can find products that are labeled as hand soap or liquid soap, and then you look at the ingredients and they say sodium lauryl sulfate, which is a synthetic surfactant. There is no saponification reaction involved. The regulation here is a bit different, but I love that the FDA actually is very strict on what is allowed to be called soap and what is not. Every oil, coconut oil, shea butter, beef tallow, olive oil, contains different fatty acids profile. And those fatty acid profiles will determine the quality of the soap. Coconut oil is high in lauric and myristic acid. When it reacts with lye, it will produce sodium laurate and sodium myristate, and those are the substances that add a lot of bubbles to your soap. Olive oil is high in oleic acid. When it reacts with lye, it produces sodium oleate, and this is the substance that produces a lot of conditioning properties to your soap. That's why the most suitable soaps for sensitive skin are usually the soaps that are very conditioning, like soaps that are made with a high concentration of olive oil. Which brings me to my last point. Every oil, coconut oil, shea butter, olive oil, has a different demand for sodium hydroxide or potassium hydroxide. For example, for olive oil, the saponification value is 0.135. Meaning that you need 0.135 grams of sodium hydroxide to convert 1 gram of olive oil into soap. Every oil, coconut oil, shea butter, they have a different saponification value. And that's why having pure sodium hydroxide is helpful to determine how much lye you need to add to convert your oils into soap. And luckily, we don't need to do the measurements by hand. We don't need to do the measurements on our own. We have what's called soap calculator, which are free available versions online to measure how much lye you have to add in your oils to convert them into soap. Potassium hydroxide leads to a more softer type of soap and is used to make liquid soap. Sodium hydroxide leads to a very solid soap that basically looks like this. Saponification is an amazing reaction, and saponification happens in a high pH environment because of the lye solution, which is very basic. The fact that saponification happens in a very high pH environment means that a lot of nutrients and vitamins that might exist in your oils get degraded. So vitamins like vitamin E, vitamin C, and different antioxidants, they will get degraded in a saponification environment. That's why the only thing, and basically if you want to go from someone who copies recipes to someone who understands how to design their own recipes based on their own goals, I put down together an ebook that has 15 tested recipes plus the why behind each ingredient you add in your skincare. It includes products from soap, dish soap, sensitive skin soap, shaving soap, deodorants, lip balms, shampoo bars, conditioner bars, hand creams, and so on. If you want to check the link in the description below. Thank you so much for watching all the way to the end. I hope you enjoyed this video, taking you back on the history of soap making, and I'll see you guys next time. See you guys.